700 megawatts solar power plant audit as per IEC 62446 standard. He is currently working as a technology advisor in Cargo Solar Power in Gujarat Private Limited, India. He also been an international research advisor for International Solar Energy Studies, Energy Society, Germany. And he was also there as a thermal management consultant in solar, a grid connected CU for Danfoss Industrial Private Limited, Denmark. And he was also worked in thermal storage device consultant for Philips India Limited. And he was a renewable energy subject matter expert for India for Sourceflick Consulting India, UK. And he was also like experienced in thermal system design expert for Royal Sims Company Limited, Republic of Ghana. And he was expert in SEDI Energy Private Limited, Australia. And he is also a BTMS consultant for Core Power USA. He has a very long profile. With a short profile, I would like to invite our chief guest to deliver a speech. So it's over to you.
Mr. Mayilvelnathan, that our time will be a little short. Actually, we have to complete it by 7:75 because the Zoom platform has to be given to the other meeting. They requested our same Zoom platform. So just constrain the question answer session and all will be there for only 5 to 10 minutes. So we have to close it by 7:05 or 7:10. Okay. Keep it in mind, sir. Thank you so much. I welcome you again. You can proceed with the.
Thank you, Mr. Chairman, sir, and the mind-blowing introduction by Gogul. Thank you for your introduction and all. Thank you, sir. Good evening, everyone. It's an honor to have the opportunity to address such a distinguished audience. Let me introduce myself. Dr. Mayilvelnathan Vivekananthan from Anna University in India, and also advisor for International Solar Energy Society, Germany. Okay. In this talk, I would like to concentrate on net zero emission by 2050 scenario and green hydrogen. My talk is particularly relevant those of you who are familiar on renewable energy in all levels. Okay. The executive summary of my presentation. Okay. The detailed study has been done with the various available projects and literatures. Feasibility of green hydrogen using renewable energy has been studied. Okay. The detailed review of concentrated solar thermal has been done. This is my executive summary of my presentation. Then overview. Okay. What is green hydrogen? Then how it is work? Then what does it mean? Okay. What is the difference between that green hydrogen and other things and all? Then why it is important? Then examples of green hydrogen in use today. Can it replace fossil fuels? Can it be economically viable? How it helps the environment? Okay, these are the things we are going to discuss in our presentation. Okay. Then on the why net zero emission normally by 2050, by our Indian part it is a 2070. Okay. In COP26, our Prime Minister assured that 2070 we have to achieve 100% renewable in our all areas. Okay, energy sectors. Actually, my presentation is divided by into three main parts. First point concerned define hydrogen. Second, I will focus on concentrated solar technology. Finally, I will deal with the green hydrogen. My presentation will take about 30 minutes. I can email the PowerPoint presentation to anybody who wants it. There will be a time for questions after my presentation. What is hydrogen? Hydrogen is a odorless, flammable or chemical element. Normally, after independence speak of our Prime Minister, Mr. Narendra Modi, that hydrogen is sparking in 2021. Everyone wishes a new technology, new areas, new growth. The development of hydrogen on a large scale and addressing climate issues is the main target on many countries. To achieve the hydrogen goal, they need adopt advanced technology because hydrogen is an odorless, flammable chemical element only. Hydrogen is represented by a normally letter hydrogen. The atomic number is 1. The water is known as hydrogen source. Okay, normally water is a hydrogen source. Water is a combination of hydrogen and oxygen. Already you know. The surface area is 71% of Earth covered by the water. Okay, out of 71% of water, 97% covered by seawater and 3% fresh water. So the source of hydrogen is huge. Okay, the water is an essential part of our life. Here, normally the hydrogen is a clean, green energy. Then hydrogen energy is highlighted on a energy strategy spectrum. Normally, the highest potential, hydrogen having that highest potential compared with the other energy resources. And normally, the fuel weight, the weight of compared with that fuel weight of petrol and all, if you take a hydrogen. So the hydrogen having highest energy content compared with other fuels and all. Okay, then it can easily transformable. Okay, so it can convert it into ammonia and all. Okay, it can be used in the various applications and all. Okay, so these are the applications. Another one, the hydrogen is a clean energy and the green energy. Why you are telling clean and clean energy? Clean energy means the normally any fuel it makes some emission. Okay, that emission having carbon, it's mean it's not a green energy or clean energy. Okay, if you having clean for hydrogen, if you make a fuel hydrogen mean if you burn the hydrogen, the output, the emission is only water vapor. So water vapor will not harm the environment. So water vapor not having any carbon content, so it will not affect the environment. So it is an environmental friendly, green and clean energy. Okay, that's why all are choosing this energy as a source of future. Okay, then types of hydrogen is a very important part. Okay, the hydrogen developed roadmap. This is a roadmap of hydrogen development. Is very important for achieve our targets. Okay, normally in the roadmaps like green hydrogen. Okay, the green hydrogen itself, the hydrogen produced using energy from hydrocarbons, normally natural gas with the carbon dioxide emitted as a part of the process. So gray hydrogen, it is a hydrogen normally produced from the using hydrocarbon. Normally natural gas is a source, but natural gas is the source of hydrogen protection. The exhaust is a hydrogen, but the product is hydrogen and the exhaust is a carbon dioxide. Again, it will damage our environment. Then we'll go for a blue hydrogen. Blue hydrogen is same. The hydrogen produced almost emission free from your using carbon capture and storage technology. Okay, CCUS. Okay, CCUS. CCUS is a carbon capture and storage and utilization. Okay, these are the CCUS. Normally, if you are using CCUS, okay, the natural gas as a input, okay, input or a source of hydrogen protection. The output is hydrogen. Output is hydrogen. Then exhaust. Okay, the exhaust is a carbon dioxide. It can be stored in underground or it can be used for further usage. Okay, so we can get the hydrogen from that natural gas, but the carbon dioxide emission can be reduced. So remaining hydrogen only. Okay, the product is hydrogen, pure hydrogen. So it is called blue hydrogen. Okay, then green hydrogen. The green hydrogen is our part. Okay, so hydrogen made via electrolysis with at almost emission-free process. For example, see the figure. It is green electricity passed over this. Okay, so green electricity means the electricity from our renewable part. It may be a solar, it may be a wind, or it may be a geothermal, or it may be any other renewable sources. So we can heat the water. The water is split into hydrogen and oxygen. So there is no byproduct is there. Only hydrogen and oxygen. So it will not affect that our environment. That's why we are telling that it is a green hydrogen. Okay, the green hydrogen. Okay, next slide. Okay, okay, next, how it can be used. Okay, so various applications of hydrogen is there. So it can be used in industry or transport or building or electricity generation. Okay, so in industries like iron and steel industry or chemical industry, other industries are using green hydrogen as a heating fuel. Okay, so then transport is used for LD road or HD road or shipping or others like that. Then buildings, the buildings, it may be a for example SOFC or PEMFC like that. Then electricity generation. So hydrogen blending with natural gas, we get gas turbine. Okay, blending in natural gas turbine, we can produce a power. Then high temperature fuel cell, we can use high temperature fuel cell. Then pure hydrogen gas as turbine. There are hybrid fuel cell, gold gas turbine system. Already, if you have a system, that system we can adapt hydrogen as a fuel. Okay, so we can produce the power. So these are the 4 categories of hydrogen applications. Like in the first one, feedback from this is the hydrogen production industry. So it can be directly used to produce ammonia or methanol or refining plants and all. Okay, so next one, the delivering heat to the buildings. Okay, so in the building concept, we can passive heating and all. So passive heating and all, we can use the hydrogen as a fuel. Okay, then the source of energy for high temperature process. So petrochemical, refining, steel or cement like that. Okay, then we go for the fuel for heavy transport, including heavy duty trucks. So heavy duty trucks are nowadays used in United States of America. Most of the they try to do that. Okay, they are making some trucks using hydrogen as a fuel. Okay, then hydrogen used in industrial applications. Already I mentioned that the industrial application of hydrogen. Okay, very important part, because nowadays we are using natural gas 186 is a dedicated protection, then byproduct of hydrogen. So in the dedicated protection, hydrogen gas 186 metric ton hydrogen is produced by natural gas. Then 75 metric ton nowadays. Okay, usually 75 metric ton of hydrogen produced by coal, and 2 metric ton of hydrogen using oil and electricity, others and all. So totally the 69 metric ton of hydrogen, of which 0.4 metric ton of hydrogen produced with the CCUS. Already I told that because CCUS is carbon capture utilization. Okay, so and storage. So this 0.4 percentage only nowadays we are using CCUS. Okay, so that 69 metric ton we are used for refining plants. Then other remaining is 31 percentage by ammonia. Then 0.1 percentage only metric ton only metric ton hydrogen only produced with the renewables. Okay, so these are the things. Okay, the demand for pure hydrogen. So the pure hydrogen, where it is used, the 38 metric ton of hydrogen nowadays used in a refining plant, 31% metric ton of hydrogen used in ammonia making, then 0.01 metric ton used in a hydrogen used for transport purposes, and 4 metric ton hydrogen used in other purposes and all. So then demand for hydrogen mixed with the other gases. So 12 metric ton hydrogen for used in methanol, then 4 metric ton is a TRI, then 12 metric ton H2 is a other gases and all. So these are the things used to do the industrial applications. I segregate all those things. Okay, then net zero emission. First topic, net zero emission. We were going for a green hydrogen. Okay, because every year 2030 or 2050, then 2050. Okay, the scenario that of 5 degrees Celsius, the increase in temperature is of sea is at 5 degrees Celsius. That's why it will increase that automatically in the glaciers or in south. Then that is in North Pole, it will melt, so automatically it will rise, the sea level will rise. Okay, so in order to avoid that, all developed countries are planning to make some norms. Okay, make some scenario. So that scenario is called net zero emission by 2050. Okay, so achieving a zero emission. Okay, achieving zero net emissions by 2050. will require a broad range of technologies to transform the energy system. The key pillars of decarbonizing the global energy systems are energy efficiency, behavioral change, then electrification, then renewables, then hydrogen and hydrogen-based fuels, and carbon capture, utilization, and storage. Okay, these are the key pillars of decarbonization. Again, I am telling the global energy systems are the key pillars of global energy systems are energy efficiency, behavioral change, then electrification, then renewables, then hydrogen and hydrogen-based fuels. These are the some key pillars. So the importance of hydrogen is the net zero emission scenario is reflected in actually its increasing share in total energy consumption. In 2020, the hydrogen and hydrogen-based fuels accounted for less than 0.1%, but by 2030 they meet 2%, and total fuel consumption for hydrogen in 2050 is around 10%. Okay, that is so in this graph itself shows that within 10% we can reach. Okay, in 2050. Okay, then the hydrogen demand by announced pledge scenario, it's a then net zero scenario. So net zero emission 2050 like that. Okay, the hydrogen demand, this hydrogen demand and all 2050. This below that some the bottom of this. So this is a metric ton of hydrogen produced. Okay, so in 2020 we are producing about 90%. 90 already we saw that. So 90 ton of 90 ton of hydrogen we are making. So 2050, so 25. So these are the up to within 2050. Sorry, 2050 we can reach 2050. Sorry, 250 metric ton of hydrogen produced by announced pledged scenario. But net zero scenario we are now producing same way 90 metric ton. So in 2050 we can reach that 50 metric ton of scenario. So bottom of that slides and all. So refining, ammonia fuel, then synchronizing building section. So these are the some field of applications of hydrogen in that current field and all. Okay, and then low carbon hydrogen used in 2050, and total hydrogen in the project case, then this one. Okay, these are the APS and the NEZD scenarios 2020 and 2030. So hydrogen demand in the industry nowadays, it is an 65% in ammonia, then methanol 25%, and DRI 10%, and other industrial use as less than 1%. Then low carbon hydrogen protection and use, it is around methanol around this is a project case, then APS case, then NEZ case up to 2030. Okay, 2030. So these things. Then a total hydrogen demand in 2050 like that. Okay, the project case, then APS case and NECT's case. So in the uses of chemicals, iron and steel, other and the chemicals and iron and steel. So these are the things they are explained. Okay. Then hydrogen demand project case, then APS and is in a scenario in 2030. For example, in application area, like that. This one. Okay. So 2030 NEZD, this is a project case, then APS, then NEZD, then these are the some percentage. Okay, these are the some percentage: grid connection, building sector, synchronized wheel, then energy, ammonia fuel, power, transport, industry, refining, and the share of TFC. Okay, the share of TFC in NEZD, we are telling that like tax is up to 100%. In that we are achieving that our TFC should be 100% in that NEZD. Okay, we are doing that. Okay. Then these are the things: hydrogen protection through centralized reforming in that. Okay, the hydrogen protection through centralized reforming. Natural gas and the deployment of green alternatives. Okay, what are the sources are available to produce our hydrogen in our India concept? So this is a gas infrastructure in the bottom of the screen itself. So there's some gas infrastructure of India. So this using the gas, we can produce using electric grid infrastructure. So right side is the application. This side is a grid applications. It is a source of hydrogen protection. It can be used by renewables or nuclear power or fossil with carbon capture, utilization and storage, or conventional storage. Okay, you can power generation and all. So the waste heat or waste electricity can be used for hydrogen generation. This hydrogen generation can be used to for transportation purpose or synthetic fuels or upgrading oil or biomass or ammonia or fertilizer or metal protection or chemical and industrial purposes, okay, or heating purposes. These are the some applications and protection of hydrogen using natural gas deployment alternatives. Okay, so these are the things. But in this normally it is having the gas structure. The gas structure we are producing hydrogen, but the gas also is natural gas. It also produces some carbon pollution and all. So this carbon can be controlled by carbon capture, utilization and storage. Okay, CCU systems. Okay. The hydrogen protection cost. Okay, so grid electricity US dollar itself per den of, okay, US dollar for kilogram of hydrogen. Okay, so $5 for grid electricity, it is around $5.5. For renewable electricity is $3 per kilogram of. Then natural gas, it may be a $2 per kilogram. Then a natural gas with the CCUS. Okay, CCU, if you are using carbon capture utilization and storage, mean the cost will increase of protection cost of hydrogen will increase. Okay, the coal based mean it around $1 US per kilogram of hydrogen. Then coal with the CUS around 1.5. Well, small difference is there. Okay, so but in the right side itself, it is a kilogram of carbon dioxide produced by hydrogen. Okay, so these things, the point, the grid electricity. So this is a point. Using grid electricity mean it is around 30 kilogram of carbon dioxide produced per kilogram of hydrogen produced. Okay, so the renewable energy itself, it is a zero kilogram of carbon dioxide produced per kilogram of hydrogen produced. Here the $2 kilogram by using natural gas. If you're using that natural gas of the CCUS, is less in amount, nearly zero. Okay. And then coal is high. Okay, so this is a 4 kilogram of hydrogen. Normally, sorry, 20 kilogram of carbon dioxide produced per 1 kilogram of hydrogen. Okay, imagine that it's a very huge amount. Okay, the coal with CCUS, it's around 3 kilogram of carbon dioxide produced per 1 kilogram of hydrogen. Okay, these are the protection cost variations. Then, okay, hydrogen protection cost for a different technology options in 2030. Okay, so here also same way, the electrolysis grid. What are the terms are used in that? What are the technology used to hydrogen protection mean? There is an electrolysis process. It's an electrolysis process. It is a process we can split the hydrogen oxygen by heat source. Okay, it is automatically, it's around 1,000 degrees Celsius, and it automatically the hydrogen and oxygen atoms are splitted. So we can store the hydrogen and we can store the oxygen also. So there is a called electrolysis process using grid. Okay, then electrolysis renewables. Okay, so the compare with the see one thing, the electrolysis cost of hydrogen protection is high for electrolysis grid, but cost of hydrogen is less for electrolysis renewables. Then natural gas with the CCUS. Then natural gas with the CCUS. Normally, without CCUS, with the CCUS, somewhat slight difference is there. Natural gas with the CCUS. So we can prefer this one. Okay. Then combined sensitivity, then CO2 price sensitivity, capex and apex models and all. Okay, you know about it already. You know about capex and capital expenditure and open operational expenditure sensitivity and all. So all those things are varied. Okay, the fuel cost sensitivity. This is fuel cost sensitivity. Then carbon dioxide prices. Okay, for without CCUS having the highest carbon dioxide. Okay, coal with this is a very less amount only. These are the hydrogen protection cost for different technology option in 2030. Then go for CO2 intensity is very important because of we are using is a hydrogen. We are protection. We are main aim of protection of hydrogen is to avoid the pollution in the environment. That's why the CO2 intensity of hydrogen protection is very important. That's why the hard coal, if you're using hard coal used for protection of hydrogen mean it with CCS 90% capture rate mean it's very less. Okay, without CCS around 20 kilogram of carbon dioxide produced per kilogram of hydrogen. Okay, for natural gas and 90% capture rate is there, so it may be very less. The natural gas with the CCS around 56% capture rate is there. So without CCS it's at around 9. Okay, then electricity, renewable or nuclear generation, then gas-fired generation, then coal-fired generation, and world average electricity mix. These are the things. The coal-fired generation having the 40 kilogram of carbon dioxide produce 1 kilogram of hydrogen. Okay, so this is an important thing we have to consider before designing a hydrogen protection system. Okay, then selected project operative. Now these are the projects operating refining plants. Okay, petrol refineries or oil refineries. Okay, these are the hydrogen protection plant. Okay, so horizon of oil sands under Canada. Then these are the Port Arthur in the US. These are the some plants operation in world. Okay, so okay. Next thing, the hydrogen protection cost in different parts of the world. Okay, the Australia, and this is the electrolysis, renewables, natural gas, the carbon capture and utilization, the natural gas without, then coal and coal without CS. So Australia having the less, I think so. Then Chile and China having very less cost is there. So the Japan having that highest one. Okay, the electrolysis renewables having that highest. There's a $6 per kilogram of hydrogen. Then for India itself, it's around electrolysis around 2.5 US dollar per kilogram. Our main aim is to using electrolysis with renewables. We have to provide hydrogen per 1 kilogram of hydrogen by $1. Okay, this is our last meeting of electricity minister, I think so. He told that 1 kilogram of hydrogen should be make by $1. The cost of the 1 kilogram of hydrogen is $1. Okay, that's our aim of. Okay, then so it's nearer to that only, no problem. Okay, these things we are nearer to this. So to 2030 we have to achieve this target. Okay, then hydrogen is a great potential. Export potential is there. So hydrogen, so the resource is everywhere, anywhere else. That everywhere the resources is there. Okay, like a sun. Okay, like a wind. Okay, wind also it's having some seasonal things are there, constraints are there. So solar also in daytime only available, night time it's not available. So but water is available in any time. Okay, anytime. So sea water is there. We can using sea water, we can split the hydrogen and oxygen. So produce that hydrogen also. So anywhere we can make a hydrogen plant. Okay, so no need of location constraint is there. So can select a water source and all, we can put a plant itself. But where is the technology available, advanced technology available? They will only provide a plant. Okay, they will only make the plant. Like our India itself, 5 people, 5 great people like Reliance and Adani and Gale and L&D and Indian oil corporations. They are planning to make some plant in India itself. Myself as advisor for L&D, L&D mean for green hydrogen. So I sent a proposal also for this. So I connected with the Tynasset. It's a technology partner. The technology is available in Canada. They are having that. They are making some research and development in hydrogen electrolysis process. So they are our India technology partner. So green hydrogen is the future for India. Okay. So what first the process is, water is first purified. Then water is splitted into hydrogen and oxygen using electrolyzer and electric current. Okay. Then electrolyzer is powered by solar, wind, tidal energy and all. Okay. Then the hydrogen is compressed or converted into ammonia or synthetic natural gas for transport. Because of hydrogen, we are in order to make some specialized storage tank. Because of you have to for a cryogenic tank control. Because of in order to save that store the compressed nitrogen, we need some cryogenic. So we can convert this nitrogen into ammonia. So we know or a synthetic natural gas SNG and all. So we can easily transport those. Then compressed nitrogen ammonia or CNG shipped abroad to use the recovered to hydrogen. So reconverted into. So transportation, you are using an ammonia and synthetic natural gas SNG. Then after transportation, okay, reach the point, we can reconvert that hydrogen into reconverted SNG into or ammonia into hydrogen. So these things are we are having the very much export potential under. Okay, this is a simple diagram to splitting two-step method of water splitting process. Okay, so the solar energy hit that water, automatically converted into water and hydrogen. Okay, these are the things you can using the solar energy directly to the hit the electrolyzer. So it will convert that because of we need 100 degrees Celsius in the top tower. So it's a solar tower, the thousands of mirrors around the tower. It will reflect the sunrise and concentrate on one point. This point can be heated by 1000 degrees Celsius. So this heat can be split the hydrogen and oxygen. Okay. Kindly mute, sir. Kindly mute participants. Kindly mute your audio. Okay, thank you. Okay, oxide then it converted into oxide and oxygen and hydrogen. Okay, so these are the direct solar thermal chemical water splitting process. Okay, so here in green hydrogen. Now only we are coming to the point. Green hydrogen. So the green hydrogen normally the CSP collectors, then electricity generation. So the electricity generation by wind, the electricity generation by photovoltaic, then this heat. So CSP collectors, wind and all. So the CSP collector is a concentrated solar power. I will explain later. So directly we can use that solar heat to the splitting process, electrolysis process. Otherwise, we have to supply the electricity through wind or photovoltaic. Okay, so this water can be splitted. Then this water is passed over that hydrogen storage tank. It is a cryogenic tank. Okay, this cryogenic tank we can convert the hydrogen into ammonia. This ammonia can be used for agriculture purpose. This ammonia can be transferred through the ship and up. Then the hydrogen can be supplied to the natural gas network SNG and up. Then end use it's a industrial applications or vehicles and okay, for transport application. This is the concept of green hydrogen, because we are using the electricity by not a grid electricity, by using only CSV is a concentrated solar power, or it may be a wind, or it may be a photovoltaic. Okay, this is the heating or power generation like that. Green hydrogen application of green hydrogen. So due to some time constraint, I go faster. So solar field canal, it is a hybrid solar, because in daytime we can give the power to the electrolyzer by solar photovoltaic field. In a night time, we need without using any battery and all, we can use this type of concentrated solar field. This heat can be stored in a hot storage tank. This hot storage tank we can supply the we can run the expander, or it can be a turbine and all. So the turbine rotates, the turbine is connected to the generator. The generator is produce the power. So 24/7 we can give the power by using hybrid solar PV CSP technology. So technology, then we'll go for a concentrated solar power. Concentrated solar power, it's a new technology. It's not a new technology. Already we are using this technology. You can use it to produce electricity, heat, hydrogen, then energy from waste and desalination. Okay. these are things, so comparison between that some technology available. So previously in 2004, okay, the power produced by that coal by 50%. Nowadays it's only 19.68%. But renewables, it is only 9.2% in 2004. Nowadays it is in 2020 19.68%. So increased. These are some countries around facing the multiple challenges in the energy sector. So the trends and all. So what are the challenges and how we are fulfill that energy demand by renewables? Okay, the 2050 all the renewable mixes, that is our concept. The 2050 scenario is there. So 7% by solar power plant, all power needs satisfied by that our renewable energy sector. So these are the some split of projection of 2050 projection, okay, scenario. So then contribution of concentrated solar power in the global energy transition. This is useful to lots of, it is a solar store the solar energy at low cost. For this for this technology, so normally this using this technology not need any battery, okay, electric battery. You can use only the thermal storage material. You can store that heat in daytime, and it can be used for night time also. So 24/7 we can get the energy from solar. Okay, so these are the some concentrated solar power development in the path 1982 to 2030. So it's a 1982 only started. Then nowadays the 1 gigawatt, nearly 5 gigawatt operational in 2016 itself. Okay, so these are path of concentrated solar power. Then this is storage provided the CSP and thermal energy storage plants and so where it is available, okay, where it is can put a plant itself. So these are the world map of you know about it, direct normal irradiation. So the DNA is a very important, because of DNA, based on the DNA only you can put a solar concentrated solar power. So in our India we are having this potential in Gujarat and Rajasthan. Okay, so the electricity CSP plant shares in electricity consumption in countries like Australia, then Central Asia, the United States, like that. So in 2020, only 5% share is there. In 2050, it is share of this one CSP is a 40% in 2050 scenario. Okay, these are regions where CSP is excellent or normal, okay, available in there. So these are the things the CSP implemented in various regions in the world. It's Morocco, Spain, Israel, and United Arab Emirates. Then India having that this much. Okay, this is a 550 megawatt. Then South Africa is the 555 megawatt. Then Chile 1210 megawatt. Then United States 1479 megawatt. These are the technology: parabolic, then linear Fresnel, then disc parabolic, then power tower. So what is the key benefit of CSP technology? 24 hours solar. It is a CSP. Okay, it is an because of the world's most abundant renewable energy source is the sun now. Okay, so that's why you are using the sun as a abundant source. Then okay, the higher development of PV and wind CSP relaxivity enables. Okay, these are some advantages of benefit of CSP. So multi-talent, the CSP having that concentrated solar power. Okay, having that higher having that multi-talent. One is an electricity protection up to 1 gigawatt. Okay, the solar power plant is available now. Then hybrid power plant with the PV and the wind. Then for green electricity, then thermal storage up to 1 gigawatt hour we can store the heat. Okay, then lateral heat storage heating. It can be green heat for local district heating network, and a temperature from 60 to 160 degrees Celsius we can get. Then cooling and air conditioning of residential and commercial industrial areas. Then a seasonal storage. Then process heat. The temperature from 90 to 430 degrees Celsius. Then for industry, breweries and food industry. Then chemical. Then pharmaceutical industry, paper industries. Then seawater desalination. Then salt thermal, enhanced oil recovery. Then hydrogen. The cheap green electricity for electrolyzers. Okay, then contribution to high temperature electrolysis, then process heat for further processing of hydrogen into product such as ammonia or methanol. Okay, these are the applications of CSP. I think that that's why we are telling that this is a multi-talent. Okay, then as a multi-talent, it is a CSP power plant. Okay, so CSP power plant is an this is a solar field. then a storage field, then power block, okay, then heat exchanger, like that. Okay, so in that collector field, so collector field produces on the high temperature, solar high temperature. It can be saved in that hot salt tank, then gold salt tank. Okay, so in the gold salt tank, it may be that feedback from that. Okay, so the turn back from turbine, it can be stored here. Okay, these are the CSV multi-talent power plant. The CSV multi-talent is a line focus and point focus. Line focus, the parabolic trough and the linear Fresnel collector. Then point focus is a parabolic disc collector and a central receiver. Okay, then our thermal storage, how we are store that thermal energy into that. So these are the total 10 to 20, nearly 21.1 gigawatt hours of heat energy storage through that technology. Then attention of today's batteries and thermal storage offers. No, so the thermal having the highest temperature, molten salts are used for storage material. Then molten salt or thermal oil. Then electrochemical, it may be a lithium ion battery, or these are the things are used for electrical and all. So these are the things. The, for example, in 10 megawatt only we are used for this one. Then and up to 100 megawatt in days calculation, thermal storage is there. So pump storage having the highest potential. Okay, in month itself we can store the energy. Then commercial readiness of technology available in that. Molten salt is as a storage material. Then a system rating of the potential discharge time, the rated capacity, various technologies like a batteries having the highest one. So the energy management, bridging power and power generation. The same way the molten salt also used. Okay, so these are the some cost analysis of thermal energy storage material. So this is a molten salt thermal energy storage aware. It's an installed in global manner. So it's a China, and we are not having that this type of technology. So I myself as a consultant for this company, okay, Cargo Solar in Kutch itself, Kutch in Gujarat. So we are making 25 megawatt with 9 hours of storage. Okay, thermal storage system. Okay, and then thermal energy storage system, power sector. What is the power sector? Then power sector, what are the innovation potential is there? So this is the price of solar thermal system, solar energy. Okay, this is a main important thing because is an energy field by wind offshore, then wind onshore, then PV global. These are the green energy, no? So all the things are green energy. So in the we are assumed that electrolyzers efficiency is 50%. So these are the some assumptions are there. So using this one again, the offshore and the CSP with the storage, then PV-CSP hybrid. So these are things. Okay, and the cost is around 0.2 yen per kilowatt hour. So these are things. Okay, thank you for listening. Any queries, please ask.
Dr. Mayilvelnathan.
Yes, sir.
See, when you are mentioning about your kind of engagement with L&T and all that,
okay,
you are talking about this electrolyzer technology, you are looking abroad and all that. I just want to share one information.
Okay.
Just yesterday, day before yesterday, I saw a news item that the BPCL, Bharat Petroleum has got into a collaboration with this BRC, Baba Atomic Research Center, who is supposed to have developed a very cost-effective indigenous electrolyzer. Have you heard about it, sir?
They are developers. Yes, sir. Yes, sir. Yes, sir.
BRC. So I thought you can look at indigenous solution instead of going abroad. That's what I thought. Then secondly, because the time is short, I know you had to cover a lot of things in the short time. I know the going was very fast. You can give your presentation to Iei Tamil Nadu State Center. I will collect from them one copy.
Sure.
See, I have got a broad question. I don't know if you can answer. If you can answer, fine. You see, if you look at India, for example, today, when we talk about net zero emission, see, we are using 1,000 million tons of coal every year, and about 300 million tons of petroleum crude every year. See, if these two things are replaced, I think all your requirements will be taken care of. If these two things can be replaced with some renewable material. Either renewable coal or renewable oil or anything, all solar energy or, this, biogas. Now, CBG program, Government of India has got a huge program. Government of India talks about electrical vehicles and all that. Fundamentally, it is 1,000 million tons of coal and 300 million tons of petroleum.
Okay.
How do you replace both of them with hydrogen?
Not only hydrogen, it's only 20, normally the world target is 2050. But our target is 2070. Okay.
Okay. See,
yeah,
I only thought when the Prime Minister announced 2070,
okay.
I thought the globe should be alive up to 2070.
Yeah.
We seem to be running to a risk.
Yeah.
So I feel India should, okay, whatever they have said 2070 and all that, we should gallop to do before 2050.
Okay.
If possible.
Okay.
So my fundamental question is, see, even to produce hydrogen, you need electricity, isn't it? From water or whatever. You need electrolyzer, you need electricity for that.
Okay.
So how are you going to address these 1,000 million tons of coal to be replaced and 300 million tons of petroleum to be replaced?
Sure, sir. Normally, in please see this screen, sir. It is a 50.7% of coal used in 2004, sir. And nowadays, only 19.4% are used.
Hey, what are you talking? Even now, 80% of Indian energy is produced from coal only.
Yes, sir.
See, recently there was some shortage of coal and there was a hue and cry.
Yeah.
Power plants are running out. There is no coal available. It's only available for 2 days, 3 days, 5 days. Our Tamil Nadu minister giving statement and whatnot.
Yes, sir.
If you don't have coal for 1 day, you are finished.
Yes, sir.
And I'm telling you, the 2019 figure.
Okay.
Is 1,000 million tons of coal. That's about 500 MTOE.
Okay, sir.
Million tons of oil equivalent coal.
Okay.
That is 1,000 million tons of coal every year.
Okay.
They're talking about increasing the coal mining because the power demand is going up.
Yeah.
So where are you talking 17% and all? I think it requires a more serious analysis. I know it can't be done in half an hour or 45 minutes.
Yes, sir.
I mean, I'm also into this renewable area.
Okay.
That's why I know whenever people talk about solar energy potential in India, they take the entire geographical area of India as potential. But sun has got to produce food and so many things. It is not only to produce electricity.
Yes, sir.
Actually, sun has got so many other works.
Yes, sir.
That's why I always propagate rooftop solar, where the sun is getting wasted.
Yeah.
See, anyway, I mean, let me not take too much of time. These were the two concerns. Number one, the indigenous availability.
Thank you very much, Mahadevan. Thank you very much.
Sir, can I ask a pointed question? L&T collaboration you have said with electrolyzer.
Mayilvelnathan, can you close your screen?
Okay.
So that the people can be.
Sir, with L&T, which company is collaborating for electrolyzers?
In Canada, sir. Canada.
Which company? Canada in.
Yes, sir. It is confidential. Yes, sir.
Okay.
3 days before only I sent that quotation.
Okay, but only 3 days ago, L&T chairman had said we are looking into whether we should go in for electrolyzers or not.
Yeah. Yes, sir.
Achha, so nothing is final as such.
Yeah. Yes, sir.
Okay. And what about waste to hydrogen? Actually, in India itself, many technologies are there who can produce hydrogen at much cheaper than this $1 per kg even today.
Yes, sir.
So what you are doing as advisor to L&T to promote such technologies here in India?
Okay. Actually, we are doing electrolysis. All the people are using electrolyzer technology. Okay, to make a hydrogen. Okay, because of electrolyzer itself, we can make a hydrogen in small scale itself. Okay, no problem for that. But in large scale itself, my advice is to directly you can use solar energy, solar heat. My research going on in this field only.
But that is costly, na? CSP is 3 times more costly than this PV.
PV, no?
PV, as on today, because you have to have mirrors, which glass is short in supply.
Yes, sir. Another one is temperature. We need that up to 1000 degrees Celsius.
Yes.
1000 degrees Celsius. So directly can hit that sunlight into water. Okay. So directly.
But my submission is we should go for. We have to go for waste remediation in any case. Waste is increasing.
Yeah.
And if we can do it by producing renewable fuels like hydrogen, methane in a cheaper way, because through biomethanation, the cost is low. And the last stage of biomethanation, which produces methane, that is methanogenesis. Before that, it is hydrogen only. So if we extract hydrogen from that stage, it is less than 60 rupees per kg.
Yeah. Yes, sir.
So
it's less than $1, no?
Yes.
Less than $1.
Much less than that.
Yeah. Yes,
so because methane itself is costing less than $1. So if you
go for a methane
hydrogen
mean,
before that.
If you go for a methane mean, it's a carbon. Again carbon.
Yeah. So
I'll
like to connect with you and let us try to advise L&T for waste to hydrogen.
Okay. Sure, sir.
Thank you. Sir, okay. Sir, Murias Pondian, Honorary Usur Local Center. The session is nice, excellent. Sir, one kg of hydrogen only equivalent to how many liters of petrol?
Based upon the application, sir. What do you tell? How many?
Car, two-wheeler.
So $1, sir. Actually, $1. Our aim is to make $1 per kg of hydrogen, sir.
No, but in energy content he's asking, so it is 3 times.
Yeah, density. Yeah, 3 times. Yes, sir. Yes.
1 kg hydrogen is equal to how many liters?
3 times, sir. 3 times, sir. 3 times. More than 3. More than 3. More than 3, sir. Yeah.
Very good.
Yeah, density. The power density is high. Compare with that normal fuel.
3 times
better. Yeah.
Okay, good. Okay.
By weight.
Yeah, density. Density. Yeah, sir.
No, by volume it will be much less actually.
Yes, sir.
Any more questions? Any more questions from the audience? Mr. Mayilvelnathan, can you send that PowerPoint presentation so that anybody asks?
Sure, sir.
Send it to our IE office.
Okay, sure.
So that we can send it to anybody who are asking that we'll send it.
So today I'm happy, sir, because of all the genius are experienced person around me. I think so.
Anyway, nice lecture.
Thank you very much. I need your blessings also. Thank you very much.
Mr. Sivaraju, can you tell the vote of thanks?
Okay, sir. Okay, ready, sir.
Yeah,
sir, good evening to all. First and foremost, I thank our chief guest, Dr. Mayilvelnathan, Professor, Solar Expert, Mohamed Sathak, College of Engineering, Chennai, who despite his busy schedule has found time to grace this occasion. On this National Energy Conservation Day 2021, the theme Green Hydrogen. This is very informative and very useful to us. Thank you, sir. I extend my thanks to our chairman, Dr. Karupusamy sir, Joint Honorary Secretary, and Engineer Gokul, Joint Honorary Secretary, and committee members, council members, and members for making this meeting a grand success. I thank the staffs who helped with the arrangement of this meeting a grand success. Thank you to all. Thank you.
Thank you very much, sir. Thank you.
Thank you.